My name is Priya.
And I'm Anjali.
We're both software engineers on the TensorFlow team working on distributed TensorFlow. We're so excited to be here today to tell you about distributed TensorFlow training. Let me grab the clicker. OK. Hopefully, most of you know what TensorFlow is. It's an open-source machine learning framework used extensively both inside and outside Google. For example, if you tried the Smart Compose feature that was launched a couple of days ago, that feature uses TensorFlow. TensorFlow allows you to build, train, and predict using neural networks such as this. In training, we learn the parameters of the network using data. Training complex neural networks with large amounts of data can often take a long time. In the graph here, you can see the training time on the x-axis and the accuracy of predictions on the y-axis. This is taken from training an image recognition model on a single GPU. As you can see, it took more than 80 hours to get to 75% accuracy. If you have some experience running complex machine learning models, this might sound rather familiar to you. And it might make you feel something like this. If your training takes only a few minutes to a few hours, you'll be productive and happy. And you can try out new ideas faster. When it starts to take a few days, maybe you could still manage and run a few things in parallel. When it starts to take a few weeks, your progress will slow down, and it becomes expensive to try out every new idea. And when it starts to take more than a month, I think it's not even worth thinking about. And this is not an exaggeration. Training complex models, such as the ResNet50 that we'll talk about later in the talk, can take up to a week on a single but powerful GPU, like a Tesla P100. So a natural question to ask is, how can we make training fast? There are a number of things you can try. You can use a faster accelerator, such as a TPU or tensor processing units. I'm sure you've heard all about them in the last couple of days here. Your input pipeline might be the bottleneck, so you can work on that and make that faster. There are a number of guidelines on the TensorFlow website that you can try and improve the performance of your training. In this talk, we'll focus on distributed training, that is, running training in parallel on multiple devices, such as CPUs, GPUs, or TPUs, in order to make your training faster. With the techniques that we'll talk about in this talk, you can bring down your training time from weeks to hours with just a few lines of code and a few powerful GPUs. In the graph here, you can see the images per second processed while training an image recognition model. As you can see, as we increase the number of GPUs from 1 to 4 to 8, the images per second processed can almost double every time. We'll come back to these performance numbers later with more details. So before diving into the details of how you can get that kind of scaling in TensorFlow, first I want to cover a few high-level concepts and architectures in distributed training. This will give us a strong foundation with which to understand the various solutions. As we are focused on training today, let's take a look at what a typical training loop looks like. Let's say you have a simple model like this with a couple of hidden layers. Each layer has a bunch of weights and biases, also called the model parameters or trainable variables. A training step begins with some processing on the input data. We then feed this input into the model and compute the predictions in the forward pass. We then compare the predictions with the input label and compute the loss. Then in the backward pass, we compute the gradients. And finally, we update the model's parameters using these gradients. This whole process is known as one training step. And the training loop repeats this training step until you reach the desired accuracy. Let's say you begin your training with a simple machine under your desk with a multi-core CPU. Luckily, TensorFlow handles scaling onto a multi-core CPU for you automatically. Next, you may speed up by adding an accelerator to your machine, such as a GPU or a TPU. With distributed training, you can go even further. You can go from one machine with a single device to one machine with multiple devices, and finally, to multiple machines with possibly multiple devices each connected over the network. With a number of techniques, eventually it's possible to scale to hundreds of devices. And that's indeed what we do in a lot of Google systems. By the way, in the rest of this talk, we'll use the terms device, worker, or accelerator to refer to processing units such as GPUs or TPUs. So how does distributed training work? Like everything else in software engineering, there are a number of ways to go about when you think about distributing your training. What approach you pick depends on the size of your model, the amount of training data you have, and the available devices. The most common architecture in distributed training is what is known as data parallelism. In data parallelism, we run the same model and computation on each worker, but with a different slice of the input data. Each device computes the loss and the gradients. We use these gradients to update the model's parameters. And the updated model is then used in the next round of computation. There are two common approaches when you think about how do you update the model using these gradients. The first approach is what is known as asynchronous parameter server approach. In this approach, we designate some devices as parameter servers, as shown in blue here. These servers hold the parameters of your model. Others are designated as workers, as shown in green here. Workers do the bulk of the computation. Each worker fetches the parameters from the parameter server. It then computes the loss and gradients. It sends the gradients back to the parameter server, which then updates the model's parameters using these gradients. Each worker does this independently. So this allows us to scale this approach to a large number of workers. This has worked well for many models in Google, where training workers might be preempted by high-priority production jobs, or where there's asymmetry between the different workers, or where machines might go down for regular maintenance. And all of this doesn't hurt the scaling, because the workers are not waiting on each other. The downside of this approach, however, is that workers can get out of sync. They're computing their gradients on stale parameter values, and this can delay convergence. The second approach is what is known as synchronous Allreduce. This approach has become more common with the rise of fast accelerators, such as TPUs or GPUs. In this approach, each worker has a copy of parameters on its own. There are no special parameter servers. Each worker computes the loss and gradients based on a subset of training samples. Once the gradients are computed, the workers communicate among themselves to propagate the gradients and update their model's parameters. All the workers are synchronized, which means that the next round of computation doesn't begin until each worker has received the updated gradients and updated its model. When you have fast devices in a controlled environment, the variance of step time between the different workers can be small. When combined with strong communication links between the different devices, overall overhead of synchronization can be small. So whenever practical, this approach can lead to faster convergence. A class of algorithms called Allreduce can be used to efficiently combine the gradients across the different workers. Allreduce aggregates the values from different workers, for example, by adding them up and then copying them to the different workers. It's a fused algorithm that can be very efficient. and it can reduce the overhead of synchronization of gradients by a lot. There are many Allreduce algorithms available, depending on the type of communication available between the different workers. One common algorithm is what is known as ring Allreduce. In ring Allreduce, each worker sends its gradients to its successor on the ring and receives gradients from its predecessor. There are a few more such rounds of gradient exchanges. I won't be going into the details here. But at the end of the algorithm, each worker has received a copy of the combined gradients. Ring Allreduce uses network bandwidth optimally because it uses both the upload and the download bandwidth at each worker. It can also overlap the gradient computation at lower layers in the network with transmission of gradients at the higher layer, which means it can further reduce the training time. Ring Allreduce is just one approach, and some hardware vendors supply specialized implementations of Allreduce for their hardware, for example, the NVIDIA Nickel. We have a team in Google working on fast implementations of Allreduce for various device topologies. The bottom line is that Allreduce can be fast when working with multiple devices on a single machine or a small number of machines. So given these two broad architectures in data parallelism, you may be wondering which approach should you pick. There isn't one right answer. Parameter server approach is preferable if you have a large number of not so powerful or not so reliable machines. For example, if you have a large cluster of machines with just CPUs. The synchronous Allreduce approach, on the other hand, is preferable if you have fast devices with strong communication links, such as TPUs or multiple GPUs on a single machine. Parameter server approach has been around for a while, and it has been supported well in TensorFlow. TPUs, on the other hand, use Allreduce approach out of the box. In the next section of this talk, we'll show you how you can scale your training using the Allreduce approach on multiple GPUs with just a few lines of code. Before I get into that, I just want to mention another type of distributed training known as model parallelism that you may have heard of. A simple way to think about model parallelism is when your model is so big that it doesn't fit in the memory of one device. So you divide the model into smaller parts, and you do those computations on different workers with the same training samples. For example, you could put different layers of your model on different devices. These days, however, most devices have big enough memory that most models can fit in their memory. So in the rest of this talk, we'll continue to focus on data parallelism. Now that you're armed with fundamentals of distributed training architectures, let's see how you can do this in TensorFlow. As I already mentioned, we're going to focus on scaling to multiple GPUs with the Allreduce architecture. In order to do so easily, I'm pleased to introduce the new Distribution Strategy API. This API allows you to distribute your training in TensorFlow with very little modification to your code. With Distribution Strategy API, you no longer need to place your ops or parameters on specific devices. You don't need to worry about structuring your model in a way that the gradients or losses across devices are aggregated correctly. Distribution Strategy does that for you. It is easy to use and fast to train. Now let's look at some code to see how you can do this how you can use this API. In our example, we're going to be using TensorFlow's high-level API called Estimator. If you've used this API before, you might be familiar with the following snippet of code to create a custom estimator. It requires 3 arguments. The first one is a function that defines your model. So it defines the parameters of your model, how you compute the loss and the gradients, and how you update the model's parameters. The second argument is a directory where you want to persist the state of your model. And the third argument is a configuration called runConfig, where you can specify things like how often you want to checkpoint, how often summaries should be saved, and so on. In this case, we've used the default run config. Once you've created the estimator, you can start your training by calling the train method with the input function that provides your training data. So given this code to do the training on one device, how can you change it to run on multiple GPUs? You simply need to add one line of code, instantiate something called MirroredStrategy, and pass it to the run config call. That's it. That's all the code changes you need to scale this code to multiple GPUs. MirroredStrategy is a type of distribution strategy API that I just mentioned. With this API, you don't need to make any changes to your model function, or your input function, or your training loop. You don't even need to specify your devices. If you want to run on all available devices, it will automatically detect that and run your training on all available GPUs. So that's it. Those are all the code changes you need. This API is available in tf-contrib now, and you can use it. You can try it out today. Let me quickly talk about what MirroredStrategy does. MirroredStrategy implements the synchronous Allreduce architecture that we talked about out of the box for you. In MirroredStrategy, the model's parameters are mirrored across the various devices, hence the name MirroredStrategy. Each device computes the loss and gradients based on a subset of the input data. The gradients are then aggregated across the workers using an Allreduce algorithm that is appropriate for your device topology. As I already mentioned, with MirroredStrategy, you don't need to make any changes to your model or your training loop. This is because we've changed underlying components of TensorFlow to be distribution aware. For example, optimizer, batch norms, summaries, etc. You don't need to make any changes to your input function either, as long as you're using the recommended TensorFlow dataset API. Saving and checkpointing works seamlessly, so you can save with one or no distribution strategy and resume with another. And summaries work as expected as well, so you can continue to visualize your training in TensorBoard. MirroredStrategy is just one type of distribution strategy, and we're working on a few others for a variety of use cases. I'll now hand it off to Anjali to show you some cool demos and performance numbers.
Thanks, Priya, for the great introduction to MirroredStrategy. Before we run the demo, let us get familiar with a few configurations. I'm going to be running the ResNet50 model from the TensorFlow Model Garden. ResNet50 is an image classification model that has 50 layers. It uses skip connections for efficient gradient flow. The TensorFlow Model Garden is a repo where there are a collection of different models. They're written in TensorFlow high-level APIs. So if you're new to TensorFlow, this is a great resource to start with. I'm going to be using the ImageNet dataset as input to model training. The ImageNet dataset is a collection of over 1 million images that have been categorized into 1,000 labels. I'm going to instantiate the N1 standard instance on GCE and attach 8 NVIDIA Tesla V100s or Volta GPUs. Let's run the demo now. As I mentioned, I'm creating an N1 standard instance, attaching 8 NVIDIA Tesla V100 or Volta GPUs. I also attach a SSD disk. This contains the ImageNet dataset, which is input to our model training. To run our TensorFlow model, we need to install a few drivers and pip packages. And here is a gist with all the commands required. I'm going to make this gist public, so you can set up an instance yourself and try running the model. Let's open an SSH connection to the instance by clicking on a button here. this should bring up a terminal like this. So I've already cloned the Garden model repo. We're going to be running this command inside the ResNet directory. We're going to run the ImageNet main file. So we're using the ImageNet dataset, a batch size of 1024 or 128 per GPU. Our model directory is going to point to the GCS bucket that's going to hold our checkpoints and summaries that we want to save. We point our data directory to the SSD disk, which has the ImageNet dataset. And the number of GPUs is 8, over which we want to distribute or train our model. So let's run this model now. And as the model is starting to train, let's take a look at some of the code changes that are involved to change the ResNet model function. So this is the ResNet main function in the Garden model repo. First, we instantiate the MirroredStrategy object. Then we pass it to the run config as part of the train distribute argument. We create an estimator object with the run config. And then we call train on this estimator object. And that's it. Those are all the code changes you need to distribute the ResNet model. Let's go back and see how our training is going. So we've run now for a few hundred steps. At the bottom of the screen, you should see a few metrics. The loss is decreasing, steps per second, learning rate. Let's look at TensorBoard. So this is from a run where I've run the model for 90,000 steps, a little over that. So it's not the run we just started. So the orange and red lines are the training and evaluation losses. So as the number of steps increase, you see the loss decreasing. Let's look at evaluation accuracy. And this is when we're training ResNet50 over 8 GPUs. So if we see that around 91,000 steps, we're able to achieve a 75% accuracy. Let's see what this looks like when we run it on a single GPU. So let's toggle the TensorBoard buttons on the left and look at the train and evaluation loss curves when we train our model on one GPU. So the blue lines are one GPU, and red or orange and 8. And you can see that the loss doesn't decrease as rapidly as it does with 8 GPUs. Here are the evaluation accuracy curves. We're able to achieve a higher accuracy when we distribute our model across 8 GPUs, as opposed to 1. Let's compare using wall time. So we've run the same model for the same amount of time. And when we run it over multiple GPUs, we're able to achieve higher accuracy faster, or train our model faster. Let's look at a few performance benchmarks on the DGX1. The DGX1 is a machine on which we run deep learning models. We're running mixed precision training with a per GPU batch size of 256. It also has 8 Volta or V100 GPUs. So the graph shows x-axis, the number of GPUs on the x-axis, and images per second on the y-axis. So as we go from 1 GPU to 8, we're able to achieve a speed up of 7x. And this is performance right out of the box with no tuning. We're actively working on improving performance so that you're able to achieve more speed up and get more images per second when you distribute your model across multiple GPUs. So far, we've been talking about the core part of model training and distributing your model using MirroredStrategy. OK, so let's say now you've deployed your model on multiple GPUs. You're going to expect to see the same kind of boost in images per second when you do that. But you may not be able to view as many images per second as compared to 1 GPU. You may not see the boost in performance. And the reason for that is often the input pipeline. When you run your model on a single GPU, the input pipeline is pre-processing the data and making the data available on the GPU for training. But GPUs or TPUs, as you know, process and compute data much faster than a CPU. This means that when you distribute your model across multiple GPUs, the input pipeline is often not able to keep up with the training. It quickly becomes a bottleneck. For the rest of the talk, I'm going to show you how TensorFlow makes it easy for you to use TF.data APIs to build efficient and performant input pipelines. Here's a simple input pipeline for ResNet50. We're going to use TF.data APIs because data sets are awesome. They help us build complex pipeline using simple, reusable pieces. When you have lots of data and different data formats, and you want to perform complex transformations on this data, you want to be using TF.data APIs to build your input pipeline. First, we're going to use the list files API to get the list of input files that contain your image and labels. Then we're going to read these files using the TF record dataset reader. We're going to shuffle the records, repeat them a few times, depending on if you want to run your model for a couple of epochs. And finally, apply a map transformation. So this processes each record and applies transformations such as cropping, flipping, image decoding, and finally batch the input into a batch size that you desire. The input pipeline can be thought of as an ETL process, which is extract, transform, and load process. In the extract phase, we're reading from persistent storage, which can be local or remote. In the transform phase, we're applying the different transformations, like shuffle, repeat, map, and batch. And finally, in the load phase, we are providing this process data to the accelerator for training. So how does this apply to the example that we just saw? In the extract phase, we list the files and read it using the TF record dataset reader. In the transform phase, we apply the shuffle, repeat, map, and batch transformations. And finally, in the load phase, we tell TensorFlow how to grab the data from the dataset. This is what our input pipeline looks like. We have the extract, transform, and load phases happening sequentially, followed by the training on the accelerator. This means that when the CPU is busy pre-processing the data, the accelerator is idle. And when the accelerator is training your model, the CPU is idle. But the different phases of the ETL process use different hardware resources. For example, the extract step uses the persistent storage. The transform step uses the different cores of the CPU. And finally, the training happens on the accelerator. So if we can parallelize these different phases, then we can overlap the pre-processing of data on the CPU with training of the model on the GPU. This is called pipelining. So we can use pipelining and some parallelization techniques to build more efficient input pipelines. Let us look at a few of these techniques. First, you can parallelize file reading. Let's say you have a lot of data that's sharded across a cloud storage service. You want to read multiple files in parallel, and you can do this using the num parallel reads call, as when you instantiate the when you call the TF record dataset API. This allows you to increase your effective throughput. We can also parallelize map function for transformations. You can data parallelize the different transformation of the map function by using the num parallel calls argument. Typically, the argument we provide is the number of cores of the CPU. And finally, you want to call prefetch at the end of your input pipeline. Prefetch decouples the time the data is produced from the time it is consumed. This means that you can buffer data for the next training step while the accelerator is still training the current step. This is what we had before, and this is what we can get an improvement on. Here, the different phases of the input pipeline are happening in parallel with training. We're able to see that the CPU is pre-processing data for the training step 2, while the accelerator is still training step 1. Neither the CPU nor the accelerator is idle for long periods of time. The training time is now a maximum of pre-processing and training on the accelerator. As you can see, the accelerator is still not 100% utilized. There are a few advanced techniques that we can add to our input pipeline to improve this. We can use fused transformation ops for some of these API calls. Shuffle and repeat, for example, can be replaced by its equivalent fused op. So this parallelizes buffering elements for epoch n+1 while producing elements for epoch n. We can also replace map and batch with its equivalent fused op. This parallelizes the map transformation with adding the input tensors to batch. With these techniques, we're able to process data much faster and make it available to the accelerator for training and improve the training speed. I hope this gives you a good idea of how you can use TF.data APIs to build efficient and performant input pipelines when you train your model. So far, we've been talking about training on a single machine and multiple devices. But what if you wanted to train on multiple machines? You can use the Estimator's Train and Evaluate API. Train and Evaluate API uses the Async parameter server approach. This API is used widely within Google, and it scales well to a large number of machines. Here's a link to the API where you can learn more on how to use it. We're also excited to be working on a number of new distribution strategies. We're working on a multi-machine mirrored strategy, which allows you to distribute your model across many machines with many devices. We're also working on adding distribution strategy support to TPUs and directly in tf.keras. In this talk, we've talked a lot about the different concepts related to distributed training architectures and API. But when you go home today, here are 3 things for you to keep in mind when you train your model. Distribute your training to make it faster. To do this, you want to use distribution strategy APIs. They're easy to use, and they're fast. Input pipeline performance is important. Use tf.data APIs to build efficient input pipelines. Here are a few TensorFlow resources. First, we have the distribution strategy API. You can try using MirroredStrategy to train your model across multiple GPUs. Here's a link to the ResNet50 Model Garden example. So you can try running this example. It has MirroredStrategy API support enabled. Here's a link also to the input pipeline performance guide, which has more techniques that you can use to build efficient input pipelines. And here's the link to the gist that I mentioned in the demo. You can try setting up your own instance and running the ResNet50 Model Garden example. Thank you for attending our talk, and we hope you had a great I/O.